Given the graph of a function, y is equal to f of x as shown. How do you calculate the area of the region bounded by the curve y is equal to f of x, the ordinates x is equal to a and x is equal to b, and the x-axis? Actually, it's quite simple. Let's see how to do it. Begin by inscribing two rectangles under the curve within the limits x is equal to a and x is equal to b. These rectangles are taken in such a way that they cover the maximum area under the curve. Is the sum of the areas of these two rectangles the required area? No, it's not. This is because there is some area left uncovered which is above the rectangles and below the curve. Now, let's divide the region whose area is to be found into some more rectangles. Even now, the sum of the area of these rectangles is less than the area of the required region, as the shaded region is still left out. So to get rid of the region left out, we divide the region under the curve into an infinite number of rectangles, so that the curved line on the top of the small subdivisions appear to be a straight line. Observe that these four-sided figures resemble rectangles. So now, if we calculate the sum of all these rectangles, which are of negligible width, we get the required area. The width of each rectangle being negligible, we can assume that each has an infinitesimal area. Let the area of the first rectangle be dA1. Let the area of the second rectangle be dA2, and so on, and let the area of the last rectangle be dAn. The sum of the areas of these rectangles can be assumed to be approximately equal to the area of the required region. Therefore, the area under the curve between the limits is approximately equal to the sum of the areas of the rectangles. In mathematical notation, this can be represented as shown. Here, dA is the area of any rectangle, which is equal to the width of the rectangle multiplied by its height. The integration is performed from the ordinate x is equal to a to x is equal to b. The height y is nothing but the value of the curve at point y. Therefore, y is equal to f of x. Let's substitute this in the integrand. With this method, we can calculate the area under any curve. Now, suppose we wish to find the area under the curve x is equal to g of y. In this case, the limits of the integral are determined between the lines y is equal to c and y is equal to d. So the area under the curve is given by integral of g of y dy from c to d. Often we come across situations where the area of the region that we must have to find lies under the x-axis. For example, let's take the sine curve between 0 and 2 pi. To find the area of the region between the curve and the x-axis, we split the figure into two parts, as shown here. Here, the value of the function is positive above the x-axis and negative below the x-axis. Let the area above the x-axis be denoted by A1, and the area below the x-axis be denoted by A2. So the total area enclosed by the curve with the x-axis is A1 plus mod A2 as shown. Now, A1 is equal to the integral of sin x dx from 0 to pi, and A2 is equal to the integral of sin x dx from pi to 2 pi. The area can be calculated as shown. This gives the area between the curve and the x-axis equal to 4 square units. We often come across situations where we have to calculate the area between a curve and a line, as shown here. In this figure, the shaded region is bounded by the line y is equal to 4. The parabola y square is equal to 6x, and the line x is equal to 0. Let's learn a method to calculate the area of the shaded region. Begin by taking a horizontal strip of width dy. This strip will span from x is equal to 0 to y square is equal to 6x, and will cover the entire shaded region if we move it horizontally from y is equal to 0 to y is equal to 4. So the area of this region can be calculated by using the formula integral of f of y dy from y is equal to a to y is equal to b. Here f of y is the height of the strip. Observe that the strip extends from the y-axis to the parabola. So the height of the strip is equal to the function of the parabola minus the function of the y-axis. This is equal to y square divided by 6 minus x. However, x is equal to 0 on the y-axis. Therefore, f of y is equal to y square divided by 6. Now, we perform the integration within the limits y is equal to 0 and y is equal to 4. So we have integral of y square divided by 6 dy from 0 to 4. This is equal to 1 upon 6 integral of y square dy from 0 to 4. On integrating y square with respect to y, we get y cube divided by 3. Now, substituting the upper and lower limits and then simplifying, we get 32 upon 9 square units. Therefore, the required area is 32 upon 9 square units. Alternatively, the area of the shaded region can also be found by considering a strip of width dx parallel to the y-axis. The strip covers the whole shaded region when moved parallel to the y-axis, from the y-axis to point A. So the area of the shaded region is given by integral of f of x dx from x is equal to a to x is equal to b, where f of x dx is the area of the strip. A represents the x-coordinate of any point on the y-axis, and b represents the x-coordinate of point A. The strip extends from the parabola to the line y is equal to 4. The height of this strip is equal to the function of the line y is equal to 4 minus the function of the parabola. This gives f of x is equal to 4 minus square root of 6x. The area of the shaded region is given by integral of 4 minus root 6x dx from x is equal to a to x is equal to b. Now, let's determine the limits of this integral. To cover the shaded region, the strip starts from the y-axis and moves till point A. On the y-axis, x is equal to 0. so the lower limit is x is equal to 0. The upper limit is the x-coordinate of the point of intersection of the line y is equal to 4 and the parabola. Solving, y square is equal to 6x and y is equal to 4 as shown, we get the point of intersection A as 8 upon 3, 4. Hence the upper limit is 8 upon 3. Thus the area of the shaded region is given by integral of 4 minus root 6x dx from 0 to 8 upon 3. The integration is performed as shown. Now, substituting the limits as shown, we get the area of the shaded region equal to 32 upon 9 square units, which is the same as we got when we calculated the area of the shaded region by considering the strip parallel to the x-axis. Hence, the area of the shaded region can be found by any one of the two methods discussed, as they yield the same result. In earlier modules, you learned to calculate the area under simple curves and the area of the region enclosed between a curve and a line. In this module, let's see the procedure to find the area of the region enclosed between two curves. Consider two curves, f of x and g of x. Let's find the area of the region enclosed between these curves. First, divide the shaded region into thin vertical strips, each of width dx, and then perform integration over the entire region. But the question is, what is the span of this entire region? To address this, we have to observe the points of intersection of the curves. These points are the end points on both sides of the region, which can be found by solving the equations of curves. Let these points be x1, y1 and x2, y2. The area of the region can be found by using the formula integral of y dx from x1 to x2. Here y is the height of the strip, which is equal to f of x minus g of x. Here, we are subtracting g of x from f of x, because the value of the function f of x at any given point is greater than the value of the function g of x. If the graph is not available, then we mathematically check whether f of x is greater than g of x. If f of x is greater than or equal to g of x, then y is equal to f of x minus g of x. On the other hand, if f of x is less than or equal to g of x, then y is equal to g of x minus f of x. The intuition here is that height is always a positive quantity. Thus the integral to calculate the area of the region is as shown. Using this formula, we can estimate the area of the region enclosed. Let's now see the interpretation of this integral. The integral can be written as shown. Graphically, it means that we first calculate the area under the curve f of x and then the area under the curve g of x. After that, we subtract the area under g of x from the area under f of x. Now, let's take another case. Consider the graphs of the functions f of x and g of x shown here. Let's find the formula to calculate the area of the region enclosed between these two curves. In the interval a to b, f of x is greater than or equal to g of x, and in the interval b to c, g of x is greater than or equal to f of x. So we divide the region into two parts and write the integral as shown. To understand the discussion so far, let's consider an example. Suppose we have the curves f of x represented by y square is equal to 8x and g of x represented by x square is equal to 8y. Let's find the area enclosed between them. Solve equation 1 and 2 to get the points of intersection of the curves. This will help us to identify the limits while performing the integration. On solving, we get x is equal to 0 or x is equal to 8. Substituting in either f of x or g of x, we get the points of intersection as 0, 0 and 8, 8. Also from the graph, it is visible that f of x is greater than or equal to g of x between x is equal to 0 and x is equal to 8. This can also be achieved mathematically. First, express both the equations in terms of y. Now, substitute different values of x between 0 and 8 in the equations of the graphs. Observe that the value of f of x is greater than or equal to the value of g of x at all the points. Now, if we take a strip of width dx and height y, where y is equal to f of x minus g of x, then the area of the region enclosed is given by integral of root 8x minus x squared upon 8 from 0 to 8. Simplifying this integral as shown, we get an expression between the limits 0 to 8. Simplifying this further, we get 64 upon 3. Hence the area of the required region is 64 upon 3 square units.